All right, so welcome back to another fun-filled day of vector calculus. Today we're going to start moving into the last chapter, chapter 6 in our textbook, and start kind of hitting the last part of vector calculus. So up to this point, this last chapter is all about multiple integrals, and again, we have an exam next time that is basically going to be on chapter 5, so on multiple integrals. We'll talk a little bit more about that later, but just a reminder that that's coming up. But you guys did have a quiz. I haven't finished grading them, but I do want to go over it real fast while while we have the chance. So let me just go ahead and talk about that. So the very first one, at least the ones I've graded so far, went pretty well, where I wanted you to set up an integral of this function, evaluate the integral of a volume that lies under a plane, z equals 1 plus x plus y, and above the region in the xy plane bounded by the curves y equals root x, y equals 0, and x equals 1. So let me just go ahead and share a whiteboard here real fast and show you what that looks like. All right, so first let's just draw the region in the plane over which we're integrating, right? So I said it's bounded by the curves y equals the square root of x. So there's y equals square root of x, y equals 0. Let's try that again. That wasn't a very good horizontal line. Y equals 0, and x equals 1. All right, so we're looking at this region right here. So in terms of integration man being vertical or horizontal, there's not really a benefit one way or the other. I'm going to go ahead and go vertically since we already have him this way. So our bounds, if we do we're integrating 6x squared y, I'm going to do dz, dy, dx. So the y's are going to go from 0 to the square root of x. The x's are going to go from 0 to 1. That gets us this region. And then the z's, it was the volume that lies under that plane and above the xy plane. So that's going to be from 0 to 1 plus x plus y. All right, so for the first one, excuse me, that was basically the integral to get. What that answer is, I'm not really sure. We're now at a just use our calculator kind of thing. Although this one's not hard to integrate, even if you do it by hand, because it just ends up being polynomials. All right, so there was number 1. So then number 2, I wanted you to set up a double integral. This one using polar coordinates. And we wanted to find the integral of the function x squared minus y squared over the region given by x squared plus y squared is less than 4x. And I said, do not solve. So didn't need to solve this one. Just wanted you to draw it. For some reason, I lost my drawing tool. Hold on here a second, guys. Let me. I'm going to stop sharing and then we'll share again. That was weird. Normally when I share my whiteboard, I have a little toolbar that gives me options of what to do, and it wasn't giving it to me. But I got it back. So let me go ahead and show this guy to you. All right. So our function was x squared minus y squared. So if we're going to do this in polar, that's going to be r squared cosine squared theta minus r squared sine squared theta. And then because we're going into polar, we have r dr d theta, right? We always got to talk like a pirate. So r dr d theta. But now we need the region. So we had x squared plus y squared was less than or equal to 4x. And so we need to see what that region looks like. So what I would do is I would actually do this as an equation and see what that gives us. Turns out that this is a circle. So it's x minus 2 squared plus y squared is equal to 4. So it's got a center at 2, 0 with a radius of 2. So that would be this circle right here. And so for this inequality, we're looking for the points that satisfy this inequality. And you can see that the center of the circle, for example, 2, 0, satisfies it. So Seamus says, is this a homework? No, it's quiz. This is quiz number 2. It's quiz 3, problem number 2. All right, so anyway, so for this inequality, we're looking at this region in there. So what we're going to want to do is convert this into polar. So this is r squared equals 4r cosine theta, or r equals 4 cosine theta. So our bounds on r are going to go from 0 up to 4 cosine theta. Oops. There we go. And then in terms of our thetas, this is the one that caught people a little bit. We're going to want to go from minus pi over 2 to pi over 2 to get this circle. Right, minus pi over 2 would start integration man down here. He'd start rotating outward and then stop once he gets to pi over 2. Turns out you only need an interval of length pi. And the easiest is just to do minus pi over 2 to pi over 2. All right, so that is what I was looking for number 2. All right, so then if we go to the back of the quiz, numbers 3 and 4, I wanted you to change the order of integration for, let me, 1 second here. Dang it, it did it again. Oh, there we go. Okay. So let me clear all these and start anew.
So I just want to be clear. First, you converted that 4x into 4r cosine theta divided by r. R
Yep.
is equal to 4 cosine theta. But then you also
Yes.
solved the equation of the circle to find your theta bounds. Correct?
No, I found my theta bounds just by looking at my picture and seeing to map that circle. I could start at minus pi over 2 and then go to pi over 2.
Got it.
All right. So there's that guy. All right. So number 3, let me again just sort of bring this guy back up. So we have the triple integral. It went from 0 to 1, 0 to 3 minus 1/3 x, and then 0 to 6 minus 2y minus 6x over 3. And I wanted you to redo it in a different order, which is this guy right here, dy, dz, dx. All right, so for this one, first we should try to picture what this thing looks like. So this bound on top is a z bound, right? This is equals z. So if I rewrite that, I get 6 minus 2y minus 6x. 6x equals 3z. And so that's a plane. So we're going from the xy plane to this slanted plane. And then the 0 to 3 minus 1/3 x and 0 to 1 is a triangular region. This is just a trapezoid. Or sorry, not a trapezoid, a tetrahedron. So this is the same one, kind of like we've done a bunch of different times where we've got the plane angled in the corner. And that's what this guy is. So if we're going to do this in the y direction, the bounds on y are still going to be 0 to that plane. We just need to solve this for y. So it's going to be 6 minus 3z minus 6x all over 2. So those are the bounds on y. So then we need to look at the zx plane and see what things look like there. If we take that equation and let y equal 0 in this plane, we get 6 minus 6x equals 3z, or z equals minus 2x plus 2, which means in the xz plane, we've got this line, minus 2x plus 2. So I'm going to do integration man for the z. That means I need integration man vertically, right? I need z's. So he has to be lined up like that. So the bounds on this one are going to be 0, and then that line, minus 2x plus 2. And then lastly, we need the x bounds, and the x's are going to go from 0 to 1. So if we swap the y and the z, it changes the bounds thusly. All right, so any questions on that one? All right, so then that leaves us the last question, which was wanted you to change this thing from rectangular to polar. And the integral that we had here was, sorry guys. I'm having major technical issues today. I apologize. We're integrating from 0 to 4, and then 0 to the square root of 4y minus y squared, x squared dx dy. And so there's another one we want to go to polar. So I would start by figuring out what this looks like. We've got x equals the square root of 4y minus y squared, which is x squared equals 4y minus y squared, which is a circle. Again, if we rewrite this, you can complete the square. It's actually very similar to the one that we just did in, I think it was problem number 2. But this one now, it's centered at 0, 2 with a radius of 2. So that's up here. Okay, but our x's are going from 0 to the square root. So 0 to this circle, which means integration man is lying like this. So there are some examples of integration man. And then he goes from 0 to 4. So that actually gives us this region right here. All right, so when it comes time to changing the bounds on this, first, let's change our function. So x squared is going to be r squared cosine squared. If we go to polar, RD theta. Talk like a pirate. And now the r's, if we look at integration man radially here, there's an example of radial integration man. His feet are going to be at 0 and his head is going to be on the circle. So the feet being 0, it's there. The circle, we have to convert this into polar. So I would actually change it here. Go to this spot and go, that's at r squared minus 4r sine theta equals 0, which gets us r equals 4 sine theta. So we'll put that up here. And then the bounds on our angle, well, we're going to start at 0 and start rotating until pi over 2. So there is the conversion of this integral into polar. And now it's just a matter of integrating. And again, I'll leave that for you guys, but just wanted you to see the setup. All right, so there are the 4 questions from that quiz. So like I said, I'm going to finish getting those graded today, tomorrow. They'll definitely be up by some point tomorrow. And that way you can use those as a reference when it comes time to study for the exam. All right, so before I quit sharing the whiteboard here, any questions on that? Good. All right, well, like always, I will take silence as we're all good. All right, so there's that. Now, before we move on into chapter number 6, I want to give you guys the opportunity to ask any kind of questions on homeworks or anything. Anything out there we need to talk about?
Yes. What is, I forget what the exam is going to be on.
It's going to be on chapter 5. So all the multiple integration stuff.
Okay.
So conversions from one form to another, actually just doing the double integrals and the triple integrals, doing the real basic applications like volumes, areas, average values. We did skip that section, which just reminded me, I don't think I actually turned it off. But the section on centers of mass and moments of inertia, we're just going to bypass that. But it's basically just a multiple integral test.
And Jacobians, right?
Yeah,
Okay.
I consider that part of it.
Okay, cool.
Right, because the Jacobians are used with multiple integrals. It's just when we're going from one viewpoint to another. So, but yes, that's part of it as well.
Meeting is being recorded.
Sorry about that, guys. I just realized I hadn't turned on my other camera here. So, all right. So Victor has a question here. He just said, how do you make sure what's the best transformation when it's not provided? And do you mean by that, like if I were to just give you like a region or something and you have to decide on building your own, or like spherical, cylindrical kind of thing? What do you mean exactly, Victor? Okay, so building it. Okay, so some recommendations I have for if you have to build a transformation. First and foremost, use the region. Okay, totally use the region. And I'm going to share a whiteboard again just so I can show you what I mean. Okay, so if you're going to do this, usually it's the region that will tell you what to do. So for example, let's say that we're bounded by, I always want to go back to ones that you've seen. So let's actually do this. Let's just say, all right, you've got maybe this is our region. Here we go. So this is going to be y equals square root of x. And then let's go y equals square root of x, say, plus 2. That's this guy. And then we're going to be from, no, let's even do this. Let's say we're on the lines. So this is y equal negative x. And let's go y equals negative x plus 1. So the region that we're looking at is this kind of sort of looks like a diamond, but isn't, because of the fact that these are curved. Okay, so here's how I would approach this kind of question. Like if this is one I had and I had to integrate some random function inside, I start thinking about these boundaries and look for similarities. Like we got y equals negative x and y equals negative x plus 1. If I move that x over, those two are x plus y equals 0 and x plus y equals 1. So what that suggests to me is that I want to use a u equaling x plus y. Because if I do that transformation, then these boundaries become y equals 0 and y equal 1. Okay, similarly, if you look at the other ones, you have y equals the square root of x plus 2. So that's y squared equals x plus 2, or y squared minus x equals 2. The other one, y equals square root of x, that's y squared equals x, or y squared minus x equals 0. And so that would suggest to me, let's use a v of y squared minus x. So if I do these two transformations, my region now, if we were to look in the uv plane, so here's u and here's v, what that region looks like now is a rectangle. My u's are between 0 and 1. And my v's are between 0 and 2. So what I just did was I took this region that was some funky weird shape and I turned it into a rectangle. Just a rectangle in U and V. So I don't know if that kind of helps answer that question. Right, that was Victor.
Bruce, can I ask you a question about this?
Yeah, sure.
And so in this case, to find your Jacobian, I'm thinking in my head I would do the inverse Jacobian of the easier Jacobian, which is partial u according to x, partial u according to y, partial v according to x, partial v according to y, right?
Yeah, let's go ahead and finish this.
Okay.
Let's go ahead and find the Jacobian and what it would look like. So I'm going to erase the picture of the region because we don't need that anymore. Because we already used all those boundaries to form our U's and V's stuff, right? Okay, so now what we need to do is get the Jacobian. So since we've got U equals and V equals, what we're going to do is we're going to do 1 over the Jacobian that has the du dx, du dy, dv dx dv dy. So du dx is 1, du dy is 1, dv dx is minus 1, dv dy is 2y. So this is going to be 1 over 2y plus 1. Now, the one that I gave you here, we're going to have to do a little bit more, right? Because basically where we are now, we've got 1 over 2y plus 1. Let's just say we're finding area, so we don't have to worry about integrating something. But we got the 1 over 2y plus 1, and then let's just, for the sake of having something, do du dv. So the u's go from 0 to 1, the v's go from 0 to 2. But what's our problem still?
Got to replace y in terms of u and v.
Yeah, we do need to get y in terms of u and v. So this is one where we don't actually have a choice. We would have to go one step further. So probably the easiest way to do that would be to take this one that was u equals and solve that for x. So we get x is equal to u minus y, because then we can fire that down here. So we get v is equal to y squared minus u minus y. And then we could solve it for y. But because the one that I just made up for you though isn't going to really work, because you guys see what the problem is here.
Yeah, it's like a ugly quadratic.
Yeah, it is a quadratic, which means there's more than one choice for y equals. So this isn't actually a one-to-one transformation.
Bummer.
Yeah, well, that's what happens when I just make shit up, right? But here's what we'll do, just so we can. I'm going to go ahead and finish solving this for y, and we'll just use one of them. Okay, so this would be 0 equals y squared plus y minus u minus v. And so if we go to the quadratic, -1 plus or minus the square root of 1 squared minus 4ac, that's going to be plus 4u plus 4v all over 2a. So let's just go with the plus 1. Like I said, we kind of got to go with something. So let's go with y is equal to -1 plus the square root of 1 plus 4u plus 4v all over 2. Then 2y plus 1. Well, the 2's cancel, and then the 1 and the -1 cancel. So we're left with just the square root of 1 plus 4u plus 4v. And that's what would end up going underneath the 1 here in the original. So that's what this would end up looking like. This is what we would have to integrate in the UV world to find the area of that original shape. Anyway, so if I were to do one of these to you on an exam, do you like that if? If for some weird reason I gave you something like this where you had to change variables on a test that included a section on changing variables. So in that crazy alternate universe, I'm going to make sure that if there's a real natural change due to the boundaries, it's going to be a one-to-one transformation. So you don't have to worry about this plus or minus business. Anyway, But as Victor said in the chat, that was kind of what he was looking for. And in general, that's what you want to use. You want to use the region itself to drive the, you know, what transformation is going to work well. So if you think about other examples we've done, like that one that was the like diamond shape, we use those 4 boundaries, and we saw that by solving or getting the x's and y's together, there were some similarities. Or I showed you that one that had, I want to say it was like hyperbolas, right? The 1 over x, the 4 over x, and the same kind of deal. Just realize though that sometimes you don't actually have to replace both of them. And that one I was just talking about reminded me of it. Let me do this.
You mean you could do like du, dy?
No, what I mean by doing one of them is that you only have to replace one of the variables. Like we had one that was like this, where we had, say, y equals 4, y equals 1. And the other ones were y equals 1 over x. That didn't work out very well. And the other was y equals 4 over x. And so for this one, the 2 boundaries are already set for our y. The other ones, these would be xy equal 1 or xy equal 4. And so when it comes to doing a substitution here, you might say, well, let's let u equal xy, but then v is just going to be y. So that's kind of what I meant by you only have to do one of the letters, one of the change, because the other one is really just renaming it. But you would find the Jacobian in the usual fashion. This is another one where it'd be easier to do it as a du dx, du dy. So we'll have 1 over du dx, du dy, dv dx, dv dy. So du dx would be y, du dy would be x, dv dx, that would be 0, and dv dy would be 1. So that ends up just being 1 over y. But we're in that same situation where that thing is in terms of not u and v. Right? So like if we were going to be setting up this integral, we'd have our double integral of 1 over y, say du dv. It turns out both of those would have bounds of 1 to 4. But we need to replace that y. But luckily, we know y is equal to v. So we could just rewrite that as integral 1 to 4, 1 to 4, 1 over v du dv. But again, notice that it was the boundaries that really drove how I wanted to set this up. It was the region itself. And if you think about the very first time I showed you something where we changed, used a transformation to change things, the very first time I ever showed you that was with polar. We didn't call it, like we didn't go through this process at the time, right? But we were doing it. So the very first time we did that was when we did polar. And if you think about it, how do you choose when to use polar? What do you look at to
when you got circles, spheres, or cylinders?
Yeah, it's again, look at that region. Is that region circular? Right? Does it have washer shapes? Is it portions of circles? Is it, and so it was the region that totally suggested using polar. Well, yeah, that region suggested using a different transformation. It's just that transformation is one that is kind of standard, which is why we don't even really think of it as a transformation, right? Like, I guarantee you, you guys don't think about what we just did here when we do polar,
No.
right? You don't even remotely think about, oh, let's build a Jacobian, let's find the matrix and find its determinant, and then blah 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 blah. You don't even think that way because it's so standard and it's so natural to us to go with these circular regions. But it is exactly what we did here, except now we're not using circles, we're using hyperbolas. Okay, we're using hyperbolas. But that's basically the idea there. So how are we feeling about that? I think Victor feels satisfied with my answer. What about the rest of you guys? Is that decent?
Yeah.
Yeah, we're good. All right, cool. Any other questions before we dive into something new? All right, well then, hearing none and seeing none, I'm going to go ahead and switch up to the whiteboard. So this will take me just a little bit longer because I got to get my phone set up, but it shouldn't be too long. I'll see you guys in just 1 second.
Hey, Bruce,
Hey, what, Seamus?
just to clarify, the work that we're going to be covering today won't be on the exam, correct?
Correct.
Okay.
Correct. All right, so I will see you guys in just 1 second. All right, man, you should see my office. Like, I don't have a lot in here, but with my computer, I've got my earphones, my phone's got a cord, the computer cord, I've got the plug-in thing to my little whiteboard stylus stuff. They were all tangled together, and so as I started moving everything, it all fell apart on me. Chaos, I tell you, chaos. All right, so where we're going now is here into chapter 6. I'm going to introduce you to yet another kind of function. All right, so you think about so far, we looked at vector valued functions. So they were, you plug in a number, you get out a vector, right? We've also been talking about multivariable functions. I didn't introduce them to you, you've seen them before, hopefully, technically, right? But we've been using them in this multiple integration stuff. Okay, so, but there's a multivariable function. Now we're plugging in a point and getting out a number. And that point could be 2-dimensional or 3-dimensional, or as you'll see when you get into linear algebra next quarter with Larry, they can be n-dimensional. You can have a 20-dimensional point. Don't try to visualize it, but there's nothing mathematically that says we can't, right? Okay, so those are a little bit different than the functions that you're already used to, which were plug in a number, get out a number. Well, I'm going to introduce you to yet another one. So these guys are what we call vector fields. For those of you who are in physics, this isn't new. You're used to dealing with fields. But for those of you who have not taken the physics or seen it, don't worry, I'll get you up to speed real fast. Plus, for those of you who have taken physics and you're like, I know everything about fields, You probably aren't approaching them the way mathematicians approach them. So don't just start, dozing off here, because there are going to be some little nuances that are going to be kind of important. But anyway, so vector fields. These are functions. Their domain, these are going to be from R2. Now, I don't know if, and honestly, I don't remember. Have we talked about what this means, R2?
I really don't think so.
No? Okay. So R2, what this is the 2D world. So this guy R, you'll notice I made it so it's got like 2 vertical pieces to that R. That is intentional. If we talk about just plain old R with a double bar, this is the set of real numbers. So it's a shorthand way of saying that. So if we're in R2, this is a 2-dimensional, it's the set of real numbers on top of the set of real numbers. XY plane, basically. Okay, so R2, this is the 2D world. R3, this is the 3D world, and so on and so forth. So if you ever see that going forward, that's what that means. And I say if, this isn't an if, it's a when you see it. I will do it. I guarantee you Larry will do it, just because it's a fast way of describing what's going on. Okay, so for vector fields, it's going to be, the domain is going to be a subset of the 2-dimensional world. Or it can be a subset of R3, depending upon whether we want to make a 2-dimensional vector field or a 3-dimensional vector field. It's kind of like multivariable functions, right? With multivariable functions, we could be plugging in an x and a y, or an x and a y and a z, or x, y, z, and w, or, right? But we lump them all together as multivariable functions. Same thing here. Vector fields, the domains are going to be like those of multivariable functions. We're putting in points, basically. All right, that's another way to think about this, is that the domain is just a set of points. So we're going to be plugging in points from whatever dimensional world we happen to be in. All right, so that's the domain. So then what about the range? Well, the range, it's going to be a set of vectors in R, I'm going to put here Rn. So it's going to be an nth dimensional vector. All right, so saying it like this probably just like confused everybody, but here's basically what happens with a vector field. Okay, these take points and turn them into vectors. So that's what a vector field is. It's a function that takes a point and makes it a vector. Okay, so you can see where this is sort of like a combination of vector valued functions and multivariable functions, right? A vector valued function is you plug in a number, get out a vector. Okay, well, we get out a vector here. But multivariable functions were put in a point, get something out. And that's what we're doing. We're taking point and getting something out. So it's sort of a combination of the other two kinds of things we see. All right, so hopefully you're kind of okay with the idea of it. We're going to take a point, plug that point into a function, and we're going to get a vector. All right, so this is what they look like. Like here's an example of one. Let's go with f of xy equals y comma negative x. So I'm plugging in the point xy, and I'm getting out the vector y minus x. So if we were to do this for a couple of different points, like let's say we did f of 1, 2, that's going to give me the vector 2, negative 1. Or we do f of 0, negative 3. Okay, well, that's going to give us negative 3, 0, and so on and so forth. I don't think I really need to show you more examples because it's pretty straightforward how they work. All right, so this is an example of one that's taking a two-dimensional point and giving us a two-dimensional vector. But we could have had a three-dimensional point giving us a three-dimensional vector. We could have a three-dimensional point giving us a two-dimensional vector. We can go 2D to 3D. I mean, we could even go beyond 3 dimensions. I'm not going to do that to you yet. I'll let Larry tax your brain with vectors in higher order realms. But there is nothing that says that these even have to match dimensions. Okay, you can take, like I said, a two-dimensional vector or a point and get a three-dimensional vector. That's perfectly acceptable. Basically, just plug the numbers in, you get that vector. All right, so we should probably talk about all the kinds of things that we always talk about with functions. In terms of the domain is going to be all of the points where the vector actually makes sense, where you can actually construct a vector. So we look for the typical divide by 0, square roots of negatives, you know, all that good stuff. Same thing with continuity. Function's going to be continuous if each one of those component vectors, vector components is continuous, and so on and so forth. So that all kind of makes sense. But let's talk a little bit about the picture of these things. How do we graph a vector field? And what does that even mean? All right, well, think back to vector valued functions. And with vector valued functions, when we plugged in a number, we always got a vector out. And so it was a series of vectors. We ended up not drawing all the vectors though, right? Remember what we did for vector valued functions? What did we actually draw instead of all the vectors?
The heads.
Yeah, just the very tips of them, which then gave us the path and all that good stuff, right? So we didn't actually draw all the vectors. We just drew the tip of the arrowhead piece, right? If you think about multivariable functions, what we did was we extended out a dimension. You can start seeing now why we can't really approach this in either of the same way. First of all, think about drawing just the tips of the arrows. The problem is these arrows aren't defined just from one point. Remember when we had vector value functions, those arrows all came from the origin. So it made sense just to mark the tip because we knew where the other end was. It was at the origin. Now these are going to be wherever they happen to be. You give me your favorite point. At 1, 2, I'm getting a vector. At 0, minus 3, I'm getting another vector, right? So what we have to do when we graph these, oh, and you can also see why we can't really extend dimensions, because if I'm going to get a two-dimensional thing from a two-dimensional input, that means I need a minimum of 4 dimensions to see it. Well, I know I'm good, but I'm not that good. I can't see 4 dimensions, and I certainly can't represent 4 dimensions. And this is just like from 2D to 2D. Imagine we had a 3-dimensional vector going to another 3-dimensional, then we need 6 dimensions. I have no idea. So we have to approach this in slightly different way. So here's what we're going to do. When we want to graph one of these things, what you're going to do is you are literally going to graph the vector with its starting point at the input. All right, so I'm actually going to draw the graph of this vector field y comma negative x. And when I say I'm going to graph the field, I'm going to graph part of the field. I'm not going to do the entirety of it. But let me just show you with some of the example points. We already have a couple of points, so I'm going to go ahead and use those, but we'll throw in a few more, especially see if we can start seeing a pattern to this vector field, because there often are, and you can use those to help you. But let's think about this. So when we plug in 1, 2, so 1, 2, of course, is this point right here. What we need from that is a vector to negative 1. So that's going to go right 2 and down 1. So there is the vector that corresponded with that first point, f of 1, 2. All right, let's look at 0, minus 3. So at 0, minus 3, that was down here, I'm going to get a vector minus 3, 0. So that's going to point left 3 and up and down nothing. Okay, so there's another vector in this vector field. And to complete this picture, we would want to do a whole series of vectors. So let me do a bunch that are on the axes. So we just did 0, minus 3. Let's think about 0, minus 2. 0, minus 2 is going to give me the vector minus 2, 0. 0, minus 1 is going to give me the vector minus 1, 0. 0, 0 is going to give me the vector 0, 0, so that's a dot. 0, 1 is going to give me 1, 0, 2, 0, 3, 0, 4, 0. So there's a whole bunch of vectors for that. If we were to go along the x-axis, 1, 0 would give us a vector of 0, minus 1. 2, 0 is going to give us 0, minus 2, 0, minus 3, and so on. If I go the other direction, minus 1, 0 is going to give me 0, 1, 0, 2, 0, 3, 0, 4. So already, if you just look at the axes, we can get a good feel for what's going on with those vectors. The further away you get from the origin, the longer the vectors are, but it definitely appears that they're always pointing in those directions. Now, we do have one other point that we got, 1, 2. Let's do a couple more in the different quadrants, just kind of see what we get. So for example, let's do 1, 1. Or no, let's do 1, minus 1. So that's going to be down here. So as a vector, this is going to give us negative 1, negative 1, which means it points like that. All right, let's do one that's over in this quadrant. Let's do, say, f of negative 2, 3. So that one's going to give us a vector of 3, 2. So if I was over here at negative 2, 3, I'm going to get a vector of 3, 2. Does something like that. Anyway, so we just kind of keep doing this, keep plotting a bunch of vectors, and we start seeing this vector field. So this is what it means to graph a vector field. You're really just getting a feel for what's going on with the vectors when you plug in your respective points. So are you starting to see a pattern here? Like if you had to describe what this vector field looks like, What would you say? Or could you say anything?
It looks like it's rotating clockwise.
Okay, I like that for sure. It kind of looks like there's a clockwise rotation, right? Like vectors up here are getting moved in the clockwise direction and so on. And yeah, that's a great way to describe this one. This definitely looks like there's clockwise rotation with this vector field. Now, a little preview of what we're going to do. We're going to, a big use of vector fields, and some of you already know this, but a big use of vector fields is to describe motion. For example, if we're talking about an electric field, it would show us what would happen if we put a charged particle in here. Where would it want to move? It's going to follow these arrows. Or if there's a gravitational field, how does something with mass, what's it going to want to do? You could also have fields, like for me, I look at pictures like this, and my immediate thought is movement of water. Again, you guys know me and my history, and so you go, well, of course, dude who studied oceanography is going to think that way. We used vector fields to describe how water were to move, right? Like if this is the surface of the ocean and you were to drop a buoy, how's that buoy going to move? Well, it's going to follow these arrows. And so in this world, if I were to drop in a buoy, I would just see that buoy go in circles. I'd be going clockwise in circles, right? So you can describe it, use it for any kind of fluid. Atmospheric scientists use these as well. But that's really where we're going to be going with vector fields, is using them to describe motion of particles or whatever. And the tie of these to physics is pretty significant. All right, well, anyway, so this is what their graphs look like. Drawing their graphs is a big old pain, no doubt about it. So I highly recommend that you find a good online vector field grapher. And let me show you one. So I'm going to share my screen from from my computer real quick. And I'll show you what I mean. All right, good. So I see a screen. So easiest way is just go to Google and just do something like a vector field mapper, or how about grapher? And you'll get all kinds of different choices and all that. You know, I always go to Desmos. Let's see what GeoGebra gives us. I don't know if you've ever played around with GeoGebra, but it's a fun way to make or to do geometry stuff online. But anyway, so here we go. So you'll notice that this guy, we've got a vector field. And what we can do is actually just type in the formulas for our X and our Y. So this is the standard one they gave us. And of course, I'm getting a wheel of death for whatever reason.
So when I saw that graph, the base one on it's right there, it looks like the jet stream.
Okay. Looks like the jet stream. You know what I see when I see this one?
What?
I see a dipole magnet. Yeah, who was that? Just Victor just threw that in, dipole. Have you guys gotten to that in physics?
Not with magnets.
But dipoles with electric fields?
Yeah.
Yeah, so same thing with magnets, but like if you just have a bar magnet, for example, and then you just had a whole bunch of like iron filings so that they could kind of line themselves up with the vector field, you would see this sort of shape. You would get the bar magnet little chunks kind of forming this. So that definitely to me looks like a dipole, but regardless, let me show you what ours would look like. So our vector was y for the x component, and then negative x for the y component. And if you look at this, you can see the rotationness of this vector field. Also notice that the arrows are getting longer as we get further away, which is definitely what we saw as well. But definitely make use of vector field mappers or graphers, because you don't want to have to try to do these all by hand. Sometimes it's tough to see exactly what's going on. The pattern isn't always obvious. The one I gave you was pretty clear, but definitely make use of these things. It can help you out. All right, so how we feeling about what vector fields are? We doing okay there?
Pretty good.
Yeah, no big deal. All right, so these of course are in 2-dimension. You can do them in 3-dimension as well. I'm not going to even pretend to try to graph them in 3 dimensions. But you would basically do the same thing. You take your x, y, z, now we're some point in space, and then you've got an arrow pointing from it. And then you go to another point, get its arrow, another point, get its arrow, and so on. And that's how you could get 3D fields. Now, some 3D fields are really easy to spot, to see what's going on. Great examples are like gravitational fields, because all those vectors point towards the center of mass. Same thing with electric fields, magnetic fields, except they can be pointing towards or away depending upon the charges, and so forth. But 3-dimensional fields can get pretty crazy, but they behave exactly the same way. It's kind of hard to picture them. So when it comes to actually doing things with them, 3D, 2D, we don't really care. But trying to model them can be a little more complicated. But there are some good 3-dimensional vector field mappers and graphers that are available on the net that that are good enough for you to visualize what's going on. Okay, way better than anything I could draw. All right. Well, anyway, so that's what the graphs of these things look like. All right. Now, not all fields are created equal. There are some that we like better than others. And so I want to introduce you to a very important type of field. And these are what we call conservative fields. All right, just so you know, there is another name for conservative fields. I never call them anything but conservative fields. But another name for these, so also known as AKA, these are sometimes called a gradient field. You'll see why in a second. Okay, so a conservative field. Basically, this is what it means for a function to be a conservative field. We say that so I'm going to write it like this. So I've got a no, let's do this. Capital F. All right, so capital F with the arrow over it, because remember, these are vectors. We are getting vectors out. Okay, but I'm going to use capital F to show that it's a field as opposed to a vector value function. Okay, so if I've got a capital letter vector as a function, we're going to think of that as a vector field. That'll just kind of be our standard way so that we don't get confused. All right, so we say big F is a conservative field if there is a function that I'm going to call, say, little f, such that the field is actually equal to the gradient of that function. Okay, so that's what it means for a function to be conservative. All right, that's also why it's called a gradient field, because it's a field that comes from the gradient of something. So before we go too far into this, let me remind you about gradients. And there's zero judgment here, zero judgment here. Give me just a real quick hands up or say something if you don't remember anything about gradients, or maybe never even heard of them.
Last quarter wasn't the best for me, so we'll just go with no.
Okay, so Bradley's definitely on the not really sure about it. All right, Cesar's a I can appreciate that. Is that kind of a pretty common theme out there? Like gradient, you've heard the term, it kind of means something, but not really.
I think it has something to do with the partial derivative of something.
It definitely does have partial derivatives. Okay, and Victor says it's something about how a 3D surface changes. That is definitely true. The gradient has all kinds of great properties. Well, okay, let me just kind of remind you about the gradient. So first of all, this upside down triangle, this is what we use to, this is the gradient of f. And this is a vector. Okay, gradient is a vector. So I guess technically I should have an arrow over it. But what it's made out of, and I'm going to go 3-dimensional, although it could be just 2-dimensional. It could also be 4 or 8 or 38-dimensional. It's built out of the partials of the function. So if it's a function of 2 variables, the gradient is a 2-component, so a 2-dimensional vector. If it's a function of 3 variables, it's 3-dimensional, and so on. So it's good that, I like how Bradley's like, oh, it has something to do with the partials. It's good you remember that, because that's kind of the key to it. It is built from the partials. So for example, if we had a function fxy, let's just do fxy, and it's x e to the y minus x squared y cubed. All right, so there's a function f. So if we wanted to get the gradient, we would take the partials. So fx is e to the y minus 2xy cubed. Fy is x e to the y minus 3x squared y squared. So the gradient of f would be e to the y minus 2xy cubed, comma, x e to the x minus 3x squared y squared. So building the gradient is as simple as finding the partials and putting those in as the components. So do you think you could find the gradient if I gave you a function? You feel good
Yeah.
enough about? Yeah, thumbs up. All right, I'm seeing a couple of thumbs up. I like it. All right, so that's how we actually find the gradient. Now the gradient has all kinds of cool properties. One is that the gradient points in the direction of steepest ascent. So like if this function were a surface, so like let's say that this is a function that describes a mountainside, the gradient is going to always point you in the direction of steepest incline. So the negative gradient is steepest descent, right? So that's kind of a cool property. They're also always orthogonal to level curves. Level curves are contour lines, for example, are level curves. those would be places where our elevation are all the same, right? So it'd be a contour line. And so gradients are always perpendicular to those. They're always orthogonal to those. And we use that property for lots of things.
Like a
Um,
topographical map, right?
Yeah, yeah. So if you think about a good old topo map, that's showing you all the level curves, contour lines. So if you wanted to look at that and go, okay, which way should be steepest? You would basically go perpendicular to that line, and that would be the fastest way down or the hardest way up, depending upon which way you want to describe it. So another thing on a topo map, you'll see that rivers follow the gradient because water always wants to go down fastest. So streams and creeks and all that are always orthogonal. They're always perpendicular to contour lines. Don't know if you've ever noticed that, but it's the case. But anyway, so there's a lot we can do with gradients. What I need you to know right now is how we find them and what they look like. Okay. So when we have a conservative field, basically, we're looking at the gradient of some function. So let's just say, since we've got a function and we found its gradient, let's just say this was our field. Okay, this is an example of a conservative field. I know that it's a conservative field because it is a gradient of a function. I mean, I built the function. Usually we're going the other way though. Usually we know our field and we're trying to find the function that whose gradient is the vector field, but this for sure would be a conservative field. The function, this guy function f, it's called a potential function. So every conservative vector field has a potential function. And that potential function is the one whose gradient is our conservative field, right? So if this were our field, the e to the y minus 2xy cubed, comma, x e to the x minus 3x squared y squared, then this original function, this is our potential function. Okay, so that's just the terminology. So if you hear me talk about a potential function, that's what I'm talking about. It's not a function that may or may not exist. Right? It's not that kind of potential. No, this is the potential function for a conservative field. All right, so cool. The next question probably is then, given a conservative field, how is it that we're going to actually find the potential function?
Integrate it.
Yeah, I mean, obviously, if what we're doing here is we're differentiating to find the vector field, we want to find the potential field, we got, or the potential function, we got to go backwards, which means we're going to integrate. And not only are we integrating, but we're partial integrating. So you may have actually kind of forgotten about partial integrals because they were just one step along the way with multiple integration, right? They were always like the first thing we did. Well, here's another place where partial integrals matter. It's another use of them. That's not actually multiple integration. We're going to use that to go ahead and find our potential function. So like in this case, if we wanted to find that potential function, we would start by integrating e to the y minus 2xy cubed, but we're going to integrate that with respect to x. Right? And so watch what happens. The e to the y, of course, gives us e to the y times x. So x e to the y. The minus y cubed stays there, but then the 2x becomes an x squared. So you see we get x e to the y minus y cubed x squared. similarly, if we were to take the other one, x e to the x minus 3x squared, oh, except that wasn't x e to the x, that was x e to the y. X e to the y minus 3x squared y squared, and integrate that with respect to y. We're going to get x e to the y because x is constant, and e to the y, of course, it's integral to e to the y. And then we're going to get minus 3x squared times y cubed over 3, which you'll see does bring us to the same place. So this is going to be the process of finding a potential function given a conservative vector field. We're just going to do partial integrals.
Will there ever be a situation where both the integrals are not the same?
That's a very good question, and the answer is yes.
Okay.
That's actually the next thing I was going to warn you about, because it has been a while. Like, when did we first talk about partial integrals? Oh, good Lord. That was like forever ago, right? Like maybe even a month ago. There's something that didn't show up here but could have. Do you remember what the catch was when we did partial integrals?
Doesn't that plus c also become a variable?
Okay, and that's exactly what it is. Normally, not normally, but always when we integrate, we add on a plus c, right? But now this c, in the first case, can be a function of y, right? It could just be any old function of y. For the second one, this can be a function of x, because x's are constant when we're dealing with the variable y. Y's are constants when we deal with that variable x. So it is very possible that these two are not equal. They will share terms. For a conservative vector field, there's the possibility that they do share a term, but there could also be other things. And those other things can be just standalones when they're not in terms of the other variable. So that is something we're going to have to watch for, and I will show you examples of that for sure. Okay, so will they always be this identical? No. And even if they are identical, we don't necessarily know the potential function, right? Because like that's not the only function whose gradient is the one that I just gave you. Because remember this whole plus c, what if that plus c was 11? Right? Put on a plus 11 over here. Does that change our gradient?
No.
No, because the constant, when we differentiate, it just goes away. So we do have to kind of remember that we're finding a potential function. We're not finding the potential function. Okay, because potential functions, there is more than one. In fact, there are an infinite number of them because we could add any old c. But it does turn out that those potential functions are, if they're different, they only differ by a constant. A constant, right? Because if we had some other function of x and y in here, it would show up with its derivatives in the gradient chunks. And so the only ones that we're guaranteed will go away are if they are constant. Okay, so just watch out for that. When we're integrating, we do open up the potential of the potential. We do open up the chance of having constants that are part of that function. Okay, well, let me show you a more complicated one, or not more complicated, but one that doesn't play out exactly like this, where we got exactly the same thing with both of them. All right, So let's do this. Let's actually go to a 3-dimensional. And let's make it look like this. So we're going to have a vector field that's given by x squared yz minus the sine of, well, then I don't want sine. Let's go minus y cosine of xy You know what? Hold on. Abort. I'm making one up as I go, and that's always a problem. So just hold on a second here. Let me try this again. So here's what I want for my components. I want, or F. Let's go with 2xyz and then we're going to have a minus y cosine of xy. All right, so that'll be our first component. For the second component, let's have x squared z and then minus x cosine xy. And then for the third component, let's have x squared y plus 4. So here is a 3-dimensional vector field. Let's see if we can find its potential function. All right, so we need to do 3 triple integrals now. Or not, partial integral. So the first one, we're going to integrate 2xyz minus y cosine of xy with respect to x. So all the y's, all the z's, those are constants. So let's see what happens here. So we get the yz. Integrating 2x is going to give us x squared. So that piece is going to give us x squared yz. All right, integrating cosine, we're going to get sine. There's going to be a minus. So we're going to get a minus sine of xy. And that y gets canceled out from the u substitution. Okay, but I'm going to put on here that we can have, I'm going to call it C1, but we can have a constant function of y and z, right? I can have as many terms that have only y and z in them as I want, and they could be there, because when I do that partial derivative with respect to x, they all go away. Okay, but I do know that the potential function has to have at least these 2 pieces in it, right? There has to be the x squared yz and the minus sine xy, but there could be more. Okay, so now we'll move to the next component and integrate it with respect to y. All right, well, the x squared z is a constant, so that's going to give me x squared z times y. The cosine is going to give me a sine. And the x's cancel. Again, when you do the u sub. Okay. But there's also the potential of having something that's only in terms of x and z. All right, so again, I know for sure that this potential function has to have these two pieces, which happen to be the same two pieces as before, right? But I know it's got those two pieces, but there could be more. All right, well, let's go to the last one. The last one's the easiest one. We have x squared y plus 4, and we're going to integrate that with respect to z. So that gives me x squared yz plus 4z plus potentially more stuff that's only in terms of x and y. All right, so here's an example exactly what Bradley just asked. Is it possible that they're not all the same? Yep. These guys are not all the same. There are definitely similarities, but they're not all identical. All right, well, now here's how we put these together. So here's what I like to do. I start with the very first one with x's, and I get the pieces that I know have to be there. I have to have an x squared yz, and I have to have a minus sign of xy.
Is this function a vector or not?
Nope, this is just a regular old function.
Okay.
Its gradient is a vector, and its gradient is this vector field.
Got it.
But it's just a regular old function, multivariable function. All right, so I'm going to put check marks by these pieces because I took care of them. Okay, so now let's go to the next function. You notice I didn't worry about the constant yet. Well, we'll talk about that in a second. So then I look at the next one, the integrating with respect to y. I need an x squared zy. Well, that's already there, right? That's this thing right here, so check. I also need a minus sign of xy. All right, I already got that. So now let's go to the z's. I need x squared yz. Got it. I also need a 4z. Okay, so let me put that in there. And we've now taken care of everything except for possible constants. All right, well, here's the deal. Since we already took care of everything with x's, y's, or z's, the only other constants that are still viable are regular constants, just good old numbers, right? 11, 37, negative 14, 6, like whatever. So all we'd have to do then is add on our plus c. And so this that's actually our potential function. So I want you to notice, like, look at the blue one, the one that had to deal with the dx. So it had the x squared yz, the sine of xy, but it didn't have the 4z. But that 4z, that was part of this constant. That's constant as far as x is concerned, and so we lost it. Same thing if you look at the red line, x squared yz sine of xy, that's those two pieces. The 4z, that's constant when it comes to y. That's why it wasn't there. Or look at this one, x squared yz 4z, that was these two pieces. But now it was missing the minus sign of xy. But that's because that was a constant as far as z was concerned. It's only a function of x and y. So all those pieces, all those constant things do get caught. We still catch them. We still find them. They just get found in one of the other partial integrals. The only constants we won't catch are those that are constant constants, just plain old number. Okay, so finding the potential function is this easy. I say it's easy. I mean, it's a simple process, right? It's just integrate, do partial integrals. Go until you've done all of them. The bigger the vector field, the more you're going to have to do, right? If it's 3 dimensions, you got 3 integrals to do. If it's 2 dimensions, you only have 2. So, I mean, there is that, but it's just integrate, 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 integrate. So, do you think you're going to be able to do it on your own?
Yeah, why not?
Because last quarter was rough. That's why not. No, I'm just using your own words, right? Yeah, hopefully you're seeing it's not that big of a deal. Okay, but let's just backtrack. Remember the very first vector field I gave you? You may not, it's not that big of a deal. I can redraw it for us here. But we started with this guy. It was y negative x. All right, so what I want to do is find a potential function for this. Easy enough, right? So if we try to find a potential function for this, we're going to have to integrate y with respect to x. Well, that's a nice quick yx. Obviously, there can be some function that's only in terms of y. All right, so we integrate minus x with respect to y. All right, well, that's minus xy, and then of course we can have some function that's only in terms of x. So think about what our next step is. Our next step is to kind of combine these. So we'd say, all right, so we got f of xy is equal to yx minus xy. We got to include those pieces, and then of course, plus some sort of a constant.
But that's 0.
Yeah, that is 0. Yeah, that's just plain old C. Okay. Well, do me a favor. Calculate the gradient of a constant. What's that vector look like?
0.
Yeah, it's
Where's
the 0
zero?
vector. Is this what we started with?
No.
Okay, so clearly there's some sort of a problem, right? Well, the problem is this guy is not conservative. So here's the deal. Vector fields, not all of them are conservative. They're just not. In fact, more often than not, they're going to be non-conservative. That's what we call them if they're not conservative. Right? So sometimes you actually have functions, some fields that are not conservative. And so trying to find a potential function is pointless because no function exists that actually does it. All right, well, I guess you chalk that up to sure, why not? I mean, that happens all the time. There are continuous functions, there are discontinuous functions. Well, why not? Why can't there be some that are fields that are conservative and others that aren't, right? So, but what we'd really like to know, is there a way to tell that they're conservative before we try to do it? Like if we could have looked at this and gone, oh, it's not conservative, and we just see that from the start, it would have saved us all this work. And if you've been playing along for the last year and a half through this journey in calculus, you should be well on board with mathematicians being like, yeah, I'm not doing extra work if I don't have to. So mathematicians started looking at this and started going, okay, what are necessary conditions for these things to be conservative. And I can give that to you. All
Does
right,
it
so
have-
here's how you can tell, right? There is a way to tell. All right, so for the 2D world, let's just call these functions m and n. Okay, so like in this case, m is y, n is negative x. Okay, so f is conservative if, and this is even bigger than just if, it's if and only if. I'll explain what that means in a second if you're not familiar with it. But f is going to be conservative if and only if the partial of the first one with respect to y equals the partial of the second one with respect to x. Okay, so if my is equal to nx. So basically, this is going to be our check. We're going to differentiate the first one with respect to x, the second one with respect to y. If they are equal, then it's conservative. If those partials are not equal, then it's not conservative. And if and only if is a really strong statement. It means it's basically an equality kind of thing. So it says that if it's conservative, you know my equals nx. If my equals nx, then you know it's conservative. It goes both directions. Right? It's kind of like the square rectangle thing. Right? A square is a rectangle, but a rectangle is not necessarily a square. That's not an if and only if statement. This one's if and only if, means it goes both ways. Okay, so let me just show you real quick with why this one fails. If we go with this example, my, the derivative of the first one with respect to y is 1, and x, derivative of the second one with respect to x is -1. Those are not equal, so not conservative. Super fast check, saves you all kinds of time, right? All kinds of time. I don't think I could go back and rewrite what the partials were for that one that we took a potential function and then built it. But if you look at those, the first one, the derivative with respect to y, is going to equal the derivative of the second one with respect to x, which tells you that it is conservative. Okay, so this is the 2D check. 2D. Because there's another check for 3D. Okay, so I'm going to call these guys M, N, and P. Let me just real quick look at the book, see what letters they use, because if they use something different, I want to match them. All right, so give me just one sec. Yeah, they do use different letters. They call it P, Q, and R. Okay, so I'm going to match what the book does, which technically the book also called these guys P and Q. So PY, QX. Obviously, it doesn't matter the names of these things. I just want to be consistent so that when you look at your notes and you compare them to the book, you don't have to do some sort of like extra translation or something like that. Okay, so here's PQR, 3-dimensional. So here is the check for this one. So F, again, this field is conservative if and only if, and by the way, this double F on the if, that is intentional. That's the shorthand for if and only if. Don't you love mathematicians? Meh. We need a new phrase. Nah, yeah. IFF. if and only if. All right. So now here is the condition that's needed for this guy. Now, there are actually three things that we need. All right. The first one is the same as what we had in the 2D case. The partial with p with respect to y has to equal the partial of q with respect to x. All right, but then there are a couple more. The partial of q with respect to z has to equal the partial of r with respect to y. And then lastly, the partial of p with respect to z has to equal the partial of r with respect to x. All right. Well, yay. I mean, I guess it's a yay. Even though we have three things to check, they're pretty fast. Finding those partials is quick and relatively easy. And it's a nice way to confirm before you bother going and finding all those partial integrals. So let's look at that 3D one that we just a minute ago determined the potential function for. And I'm going to see if I can remember what they all were. So if we think about the three different components of that function, we had 2xyz minus y cosine of xy. I think that was the first component. The second one was x squared z minus x cosine of xy. And then the third component was x squared y. I'm trying to remember what the rest of it was. Oh, plus 4? Okay, if not, we'll go with that. All right, so here's how we're going to play this out. We need all these different partials. So let's look at py. Py is 2xz minus cosine of xy plus xy sine of xy. These two pieces came from the product rule on y cosine of xy. Let's compare that against qx. The derivative with respect to x of this thing is 2xz. Again, we need to do the product rule, so we're going to get minus cosine of xy plus xy sine of xy. So I'm just going to put a check mark by this one. We see that those things are equal. Okay, then let's look at qz. The partial of q with respect to z is x squared. Well, that was nice. That was fast. Let's look at ry. The partial of the last one with respect to y is x squared. Okay, cool. Check that one off. All right, then let's look at pz. Partial of the first one with respect to z is 2xy. Rx, 2xy, and again, the 4 doesn't matter. But check. So all three sets of those partials are equal to each other. That tells me it's conservative, which means, yep, I can go ahead and find its potential function. Okay, it looks like we're out of time. So basically at this point, just think about what we talked about today. Vector fields are just functions that go from points to vectors. And conservative vector fields are special ones. They are fields that come from gradients of some kind of function. You'll see why later, why we care about potential functions versus non-potential, right? Or not conservative versus non-conservative. Conservative are much nicer. They're much easier to use. We're gonna, as we build techniques for doing different kinds of integrals and stuff, you're gonna see conservative versus non-conservative matters. But anyway, just take them for what they are. All right, so for the exam, again, remember Friday we've got an exam. So no Zoom class, right? No Zoom class. It's just get on there, do the exam. Make sure you get it uploaded onto Canvas by the time it's due. I'm opening it at the start of class, so at 1 o'clock, giving you 2 hours to do it, plus the extra half hour for technical issues. So they're uploaded by 3:30. Don't push it. This isn't a 2.5 hour test. It's a 2 hour test with half hour of techno time. Okay. So make sure they're up by 3:30. And like I said, it's going to be on chapter 5. So all of the multiple integral stuff. So know how to do double integrals, triple integrals, change of variables, polar, cylindrical, spherical, switching bounds, all that good stuff, right? And again, the basic applications, volumes, areas, things like that. All right. So with that, I'm going to go ahead and call it a day.